Hello everyone, today we will discuss two body central force problems. Here we will see that reduction of the two body central force problem is equivalent to one body problem. Here let us consider a system of the two particles of mass m1 and m2. The vector r1 and vector r2 are their instantaneous position in an inertial frame with respect to origin O, and let vector r is vector distance of mass m2 relative to mass m1. Here you can see in the diagram that it is an inertial frame and m1 and m2 are the two particles. m1 has the position vector r1 from the origin O, and m2 mass has the position vector r2 from O. The relative distance between m1 and m2 is represented by vector r, and that is equal to r2 minus r1. Let us say that center of mass has the position vector r from the origin O of the two body system m1 and m2. Now we can write vector r as equal to vector r2 minus vector r1. Let us say it is equation number 1. As we know that the two particles m1 and m2 are interacting via central force, so we know that the potential energy here will be a function of the scalar distance only. In such case we can write the Lagrangian as it is equal to kinetic energy minus potential energy. So it will be equal to 1 by 2 m1 r1 dot square plus 1 by 2 m2 r2 dot square minus Vr. Let us say it is equation number 2. The system of the two particles m1 and m2 in three-dimensional space, you know that will have 6 degrees of freedom, or you can say that there will be requirement of these 6 generalized coordinates to specify the positions of this dynamical system. In other way, instead of the 6 coordinates of r1 and r2, we can select 3 components of the center of mass position vector r and 3 components of the vector r. You also know that the position vector for the center of mass is defined as m1 r1 plus m2 r2 upon m1 plus m2. Let us say it is equation number 3. Now if we see equation number 1 and equation number 3, then we can have vector r1 as vector capital R minus m2 small r upon m1 plus m2, and vector r2 is equal to vector r capital plus m1 small r vector upon m1 plus m2. Let us say it is equation number 4. Now here we can find the velocity term for r1 and r2 vector. r1 dot will be equal to vector r dot minus m2 r dot upon m1 plus m2, and r2 dot will be equal to r dot plus m1 r1 dot upon m1 plus m2. Let us say it is equation number 5. Now Lagrangian will be here as t minus v. So t will be here 1 by 2 m1 r dot minus m2 r dot upon m1 plus m2 whole square plus 1 by 2 m2 r dot plus m1 r dot upon m1 plus m2 whole square minus vr. If we solve this equation, then we can find here Lagrangian will be equal to 1 by 2 m1 plus m2 r dot square plus 1 by 2 m1 m2 upon m1 plus m2 r dot square minus vr. Let us say it is equation number 6. Now if you see equation number 6, vector capital R is not present, so it is a cyclic coordinate. If it is a cyclic coordinate, then you know that the corresponding linear momentum will be a constant. So it means that the center of mass either is in rest or moving with constant velocity with respect to O, which is the origin of the inertial frame. So when this term m1 plus m2 r dot is constant, or it is moving with constant velocity, so we can this term from the equation number 6. So here our Lagrangian now will be 1 by 2 m1 m2 upon m1 plus m2 r dot square minus Vr. Let us say m1 m2 upon m1 plus m2 is equal to mu. Here mu is called as the reduced mass. So L will be now equal to 1 by 2 mu r dot square minus Vr. This is equation number 6. Here you can see that a two body problem has been reduced to one body problem, where mass of the body is mu, which is called as the reduced mass, and it is equal to m1 m2 upon m1 plus m2. It is also important to note that vector r is the vector distance of the particle 2 from the particle 1, and which is acting as origin O. So this origin O is moving with an acceleration in an inertial frame. This means coordinate system attached to O is a non-inertial frame. Further, if you see that your m1 is very greater than m2, then if you see your reduced mass will be equal to m1 m2 upon m1 plus m2. If you divide it by m1, then you can find that m2 upon m1 plus m2 upon m1, because this term will be very less as m2 is very less than m1. So mu will be equivalent to m2, or you can say that it is equal to m. Thus you can see that if one particle is having very high mass, then it can be reduced to a single body problem. So we can write our Lagrangian for such a system as 1 by 2 mr dot square minus Vr. So whenever we need, we may replace m by mu in case of if one body is having very high mass in comparison to other body mass. Thank you.